Howdy guys, so well actually it was a while ago, but a while ago on the forums I posted one of my physics homework problems sort of as a joke, and it turns out you guys were actually kind of interested, so I got a couple requests to do a tutorial video, so here it is. It's been a little bit late because I had finals and then I had to move out of my dorm and then I moved to Japan, but now I'm in Japan for a little bit and make this video for you. So you should see the problem sort of overlapped on the screen if I can do my special effects correctly. But before we dive into the problem, what I'm going to do is a little bit of an explanation sort of why derivatives and integrals are useful, because those are really important to solve this problem. I'm not going to go in detail and explain like everything about taking derivatives and integrals and everything they are, because that's not what this video is about. Of course, if you do want that, I can make that video, but right now I'm just going to give you, I think, the minimum that you need to understand the rest of the problem. If you've already taken Calculus 2, you can just skip this section of the video. I'll include a link somewhere that you can just skip past this. Alright, so let's get started. I've drawn here 3 functions and 3 graphs. So this is our position function. So position x, that's in one direction, like an xy coordinate. It's x with respect to time, so it tells you how the function of x changes as time changes. When we say we're going to start at 100, we're going to move at a constant speed upwards at 15 meters per second, and we're going to move with this squared relationship downwards at 5. So that's what this graph here looks like. You start at 100, you go up a little bit, and then the acceleration, this is basically gravity, this acceleration takes over and brings you down. If you notice, I rounded gravity to 10, because 9.8 is close enough to 10. I've also drawn the velocity time graph here. Velocity starts at a constant 15 meters per second upwards, and then acceleration of the negative 10 brings it downwards, so you can see how velocity behaves. And then I've also graphed acceleration. Acceleration is just constant at negative 10 meters per second. So this should be fairly, you should have seen this before if you've taken any sort of physics class before. And usually there's algebraic ways to get these functions from each other, find, position, time, and velocity, and all these sort of things. But the simpler, more effective, I think, way to do this is to take derivatives and integrals. And this has much higher application for math and physics classes later down the line, such as my modern physics class. So the important relationships are that the derivative of position is velocity, and the derivative of velocity is acceleration, for instance. So we could write this like this. We could say that velocity is the time derivative, that's what this symbol means, it's the derivative with respect to time of my position function. And then we can say that acceleration is the derivative with respect to time of my position function. We can also say that acceleration is the second derivative of position function. So these are the same thing, basically, by this definition here. So these are the relationships we can take. So we can go and we can derive and come this way to get these functions. So let me just show how to do that. The basic formula for taking a derivative, it changes a lot, but the formula is that if you start with some constant, you've got an exponent and you've got a power of the exponent. Then if you take the derivative, this becomes, you pull the exponent down, so you have n times c, and then you drop the exponent 1, n minus 1. So show you what that looks like. Let's take the derivative of our x function, which equals velocity, and that'll be 100, has no exponent, so the 100 will just go to 0, right? So 100 goes away, so you have 0 plus 15t. This, the t has a t of 1, and that t changes to 0, so this just becomes 15. And the negative 5t squared, the 2 comes down to the front, so it becomes negative 10. And the t decreases by 1, and this becomes t, basically to the first. Same thing if we take the derivative of our velocity function, which equals acceleration. We get the 15, it's got no variable, so it goes down to 0. And then this negative t becomes negative 10. And so we can go like that and find that's how these relationships that's how these equations are related through derivation. Integration is the opposite of a derivative, so it's basically you go backwards. So the integral, let's say, of integral sign of acceleration is going to equal the velocity function, and more or less, and the integral of velocity is going to equal the position function. I say more or less because it sort of gets more complicated than that. So let's take a look at it. The integral of my acceleration function is negative 10. The integral of negative 10 is going to be negative 10t plus c. Now this c is super important because the c can basically be any constant. So that's because you remember when we drive this 15, the 15 goes away. It doesn't matter what this 15 is. It could be a 20, it could be a million, it could be a negative 10. Whatever this is, it's going to disappear after you take the derivative. So when you integrate, you have to add that constant back in. You could also take a integral over a range. So for instance, let me take this arbitrary function. I'm going to take, let's take this integral from 1 to 3 of 15 minus 20t. So the way we do that, we don't need to see this time, but we'll sort of work backwards deriving. So this will be 15t minus 10t squared. All right, we can check this. The 2 comes down in front. You have negative 20t. That gets this part. And this will get that part, right? And then you take it on the bounds from 3 to 1, which means that you plug the 3 where the t is, and then you plug a 1 where the t is, and you minus those functions. So the way this will look, it'll be 15 times 3 minus 10 times 3 squared. That's one function. Minus 15 times 1 minus 10 times 1 squared. So what's this? This is 45 minus 90 minus 5. So this should be what, negative 50? Maybe. I'm just sort of doing this freehand, so if that's wrong, I'll put an annotation in. Alright, so we've basically covered, I think, the important part of what you'll need to know about integrals and derivatives to start on the problem. Let's get started. Alright, so let's get started on the real problem. I've got the problem put up on the screen. We're just going to do the first part, that part 1, because part 2 is basically the same thing, and I really don't want to do that much just number calculations. And I also put up the reference chart so you can see which one we're talking about. Alright, so the problem asks us to find this LZ. Well, it asks us to find this complicated notation thing. I'm going to ignore that right now because it sort of simplifies into something that's not so terrible to write. But we're given that LZ equals negative I h bar and then the partial derivative with respect to phi. Okay, so by the way, real fast, you see on there that it gives you that x equals r sine theta cosine phi, y equals r sine phi sine theta sine phi, and z equals r cosine theta. Basically, that means that let's see. Okay, that means that theta is the angle that, so it means that phi is the angle that is in the xy plane, this flat plane, right? So phi is going to be like depicting this angle here, and then theta will be depicting the angle that it raises above the horizontal. So rather than using like a cube coordinate system we usually use, right, where you got x goes this way, y goes this way, and then theta comes out of the, or z comes out of the page, we're using a spherical coordinate system where we have a radius. So we have this, I guess the phi angle, yeah, the phi angle that moves this way, in the xy coordinate, and then the theta, the theta angle depicts how much it raises above or below this plane, and then the radius determines how far it goes in that direction. So that's, hopefully that sort of explains the weird coordinate system that we're using if you're not familiar with it. This, yeah, partial derivative with respect to phi. So the problem, or what we're really looking for, is we're looking for this this integral here from 0 to infinity of r squared dr, the integral from 0 to pi of sine theta d theta, integral of 0 to 2 pi of d phi psi complex conjugate L hat z psi. Okay, so that's a lot. And then it tells us that we're trying to find a specific psi where n equals 2, L equals 1, and m equals -1. So that specific psi is, let me write that here. That looks like this. Psi of 2, 1, -1 equals 1 over square root of 3 to a naught. Extend this over 3 halves times r over a naught e to the negative r over 2 a naught times square root of 3 halves sine times 1 over square root of 2 pi e to the negative I phi. And I'm just going to simplify that a little bit to make it easier on us a little bit later. I'm going to take out the constants. So we're going to write this, we're going to say C. We're going to say that C equals 1 over 8 a naught to the 5 halves pi. And you can do stuff and manipulate the function and see that that's true. Or I made a math mistake and it's not true, but there's some constant. And so then we can write this phi of 2, 1, -1 as being C times r e to the negative r over 2 a naught times sine theta times e to the negative I phi. You also notice that there's this complex conjugate of our psi, which is our wave function. The complex conjugate basically means that you take all of the i's and you turn them into negative i's, and you take all the negative i's and turn them into i's. So the complex conjugate of this is going to be c r e to the negative r over 2a naught sine theta e to the I phi. So yeah, it's really simple, but that's sort of an important point. Okay, so we are looking for this L hat z, right? And we're told that it equals negative h times this this partial derivative of phi. So I want to show you, I guess, a little manipulation. If we take, and we're taking this of the complex conjugate, like this is what this operation means, basically. And since we're operating on the wave function, then we know that this times this of the wave function, I guess, is going to be, oh, there's a negative I here, negative I h bar like this of, and then we've got we've got a bunch of constants that are going to factor out, but sort of the only part that's going to stick, right? Because when you differentiate, you differentiate with respect to a specific variable. So since it's a partial derivative, our r's and our thetas, those are not going to be impacted by this. So effectively, we're looking at e to the negative I phi. And this right here is just going to be, we drop the negative 1 down, we drop the top down, right? Negative I e to the negative I phi. That's what going to be what this equals. So when you add the negative i's together, by the way, by definition, I squared equals negative 1. So we have 3 negatives, and basically we just get that this equals negative h bar of this. So that should simplify things a little bit. Okay, so moving on, let's actually solve the problem. We've got our preliminary steps sort of done. So we're looking for this of r squared dr pi sine theta d theta 0 to 2 pi of d phi, and now we've got our now we've got our, I'm gonna put this on the outside just to make things clear. Complex conjugate, negative h bar, like this, and then we can put this guy out here. So we've written our wave function and our complex conjugate of our wave function. So let's go ahead and add those in right now. Okay, so we've got c r e to the negative r over 2a naught sine theta e to the I phi, negative h c r e to the negative r over 2a naught sine theta e to the I e to the negative I phi. Okay, now if you notice, these are basically the exact same thing, except that the one has negative I phi and the other one has just the I phi. But also, we've got these three segments of integration. So this is an integral, this is an integral with respect to phi. So basically anything that's not a phi can just come out as a constant. So this whole equation, except for like this part right here and this part right here, everything else is going to move to the next bracket. And this bracket is with respect to theta. So anything that's not theta will move out to the next bracket, and then the r's will get stuck here, and they'll move out to the c's will move out to the next bracket. So I'm going to go ahead and write that like this, all in one step, because I really don't want to just waste a whole tree writing this entire problem out. So we know our constants that are not going to get trapped by any of these are going to be negative h, c, and c. So it should be negative h bar c squared. And then we have this integral. We've got r squared. We've got an r here and an r here, so r squared. Then we've got e to the negative r over 2a naught squared again. So we can drop this 2. So this will become r to the fourth e to the negative r over a naught. Moving on to the next bracket, we have sine theta here, and sine theta there, so that's sine cubed of theta. If you're unfamiliar with this notation, sine theta cubed is this. Just FYI in case somebody didn't know that. And then we've got this guy of e to the I phi times e to the negative I phi d phi. Okay, so let's just evaluate these integrals one at a time. This is actually easy because this is just 1. There's a couple different ways we can look at it being 1, but the simplest way is that if you've got, let's say you've got an exponent, we'll call it x. Let's say x to the 5. Say x to the negative 5 is the same as saying 1 over x to the 5. So here we've got e to the I phi and e to the negative I phi, which is basically the same thing as saying e to the I phi times 1 over e to the I phi, which is just 1. So this is just a 1 in this integral, which means that integrate 1, you just get phi. So this becomes phi integrated between 0 and 2 pi. So we plug in 0 and 2 pi, we get 2 pi minus 0, which equals 2 pi. Let's move on to the next set of brackets. Oh, there's a d theta here. Sorry. This next set of brackets. So if you're wondering how to do sine cubed, it's doable. You just need a trick. So the trick is that sine squared of theta plus cosine squared of theta equals 1. So then we can rewrite this part as 0 to pi of sine theta, and then we'll write the other two sine thetas, we'll write them as 1 minus cosine squared theta. Then we can distribute, and then we'll get that. I'll go ahead and distribute, just to be clear. Sine theta minus sine theta cosine squared theta d theta. And then the integral of sine theta is just going to be negative cosine theta, and the integral of this is going to be what? cosine cubed over 3. So this just becomes, this will become cosine theta, and this will become, negative cosine theta, and this will become cosine cubed theta over 3. So if we look at this, negative cosine theta, the derivative of cosine theta is negative sine theta, so that's correct. And cosine cubed, the 3 goes in front and cancels with that 3, and then we get cosine squared theta times the inside, which is sine theta. So yeah, that looks correct. And then we're evaluated from 0 to pi. Negative cosine of, well, here, let's write everything out. So negative cosine, we plug in a pi, plus cosine cubed of pi over 3, minus negative cosine of 0 plus cosine of 0 cubed over 3. Now, when we look at this, cosine of pi is negative 1. So we end up with this minus cosine of 0 is just 1. So this is negative 1 plus 1/3. When we simplify this out, this ends up as being 2 minus 2/3, which equals 4/3. And now we get on to this part of the equation. So I'm gonna just flip the paper over and write that again on the back. So we're looking at negative h squared, or hc squared, integral of r to the 4th e to the negative r over a naught dr. So to solve this, we have a handy formula called integration by parts. The integration by parts says that the integral of u dv equals uv minus integral of v du. So I'm going to say that u equals r to the 4th, and dv equals e to the negative r over a naught. And I'm going to say that du, we derive it as 4r cubed, and v is going to be negative a naught e to negative r over a naught. Okay, so then we have that the integral of u dv, which is u is r4, this is u dv, this is dr, and this is dr. So r cubed, r to the 4th, e to the negative r over a naught dr, right? U dv equals u and u times v, negative a naught e to the negative r over a naught minus the integral of v, which is negative a naught e to the negative r over a naught minus integral of v du, which is 4r cubed dr. Now we can evaluate this. Basically the same way we did it earlier. I'm going to say that u is going to be 4r cubed, which means du is going to be 12r squared. And then dv should be negative a naught e to the negative r over a naught dr, which means v equals this. By the way, let's remember that we're keeping this part and we're re-looking at this part. So then the integral of, also don't forget the minus sign. So then the integral of for our cubed, oh sorry, also dr here, and for our cubed dr, for our cubed u dv, negative a naught e to the negative r over a naught equals uv for our cubed minus a naught squared e to the negative r over a naught. uv minus integral of v du. And then you notice basically that the r value is decreasing. Each time we do it, the r decreases, and then when we get to 0, there will be, we won't get another integral, and we can actually solve it. So rather than make you guys watch all of this, I calculated this out on the side, and I'm just going to tell you the answer. Okay, so here's the answer to the problem. We've got there. If we continue doing that, you can see we've got this piece, this piece right here, which is right here. We've got this piece right here, which is right here. And basically it just keeps going until you have, you know, the r's r4, r3, r2, r1, and then we have no r, and the a goes up by 1, 2, 3, 4, 5, like this, and this e term is always there. So that's sort of where this was going, and it'll be okay. Okay, so now we have to evaluate this integral that goes from 0 to infinity. Now that doesn't make sense, but so here's how we'll look at it. Let's look at just the biggest term. I'm going to look at this, just this r4 a naught e to the negative r over a naught. I just want to look at this term and figure out what's going on. So as we go to 0, well, let's start with infinity. So as we go to infinity, this guy is going to go to a really big infinity, infinity to the 4th, and this guy is going to go to e to the negative infinity, which is 0. So you got a situation where you have infinity times 0. So this doesn't make sense. We can't really evaluate this as it stands right now, there's two ways to figure out what's going on in this problem. The first way is if you've done a lot of calculus, you can just sort of look at it, and you can realize that e to the exponent of infinity is way bigger than infinity to the exponent of 4. So basically this guy's the stronger term, so he's going to win. Yeah, he's going to win. So, or we can use, more formally, we can look at L'Hopital's rule. So L'Hopital's rule, we need to have a fraction be in the 0 over 0 or infinity over infinity. So I'm going to turn this into a infinity over infinity situation by just turning this into R4. I'm going to pull out the A. Right now he doesn't matter because he's just a constant. So we're just going to look at this, we're going to pull out the R4, and then we're going to say this is going to be 1 over e to the negative r over a naught. And this term, we can write it, as we've just discussed, e to the r over a naught. And both of these should go to infinity. Both of these are going to infinity, right? And then L'Hopital's rule says that you want to take the derivative of the top and bottom functions, and that if you do that, eventually one function will disappear. So derivative of e of anything is always just going to be itself. So derivative of r would get 4r cubed, e to the r over a naught. This one's getting smaller, we do it again. We get 12r squared over e to the r over a naught. You can see this top guy is just getting smaller and the e is doing nothing. Then we get 24r over e to the r over a naught. And then we get 24 over e to the r over a naught. And now 24 no longer goes to infinity because it's just 24. And then we have this situation where we have 1 over infinity. This is confusing for a lot of people, but 1 over infinity is essentially 0. Because, right, if you have 1 divided by 2, that's 1 divided by 3 is closer to 0 than 1 divided by 2. So 1 divided by 100 is closer to 0 than 1 divided by 2. 1 divided by 10 million is closer to 0 than 1 divided by 2. And so basically 1 divided by infinity is 0. But like infinity doesn't actually exist, so it's sort of a weird point to think about. But basically, we just know that when you've got r to any constant times e, this function is going to be, as this goes to infinity, this is going to be 0, right? So then, when we look at this function and we evaluate it at infinity, we get 0 and 0 and 0 and 0 and 0. So, coming down over here, we've got 0 minus, now we have to evaluate this function at 0. So r to the 4th is just obviously going to be 0, and then e to the power of 0 will be 1. So this term here is going to be 0, this term is going to be 0, this term is going to be 0, this term is going to be 0, and then here we have a term without any r's. So this is going to be our actual term. So then we get negative 24 a naught to the 5th, e to the negative r, and then this is times 1, right? Because e to the negative 0 is e to the 0, which is 1. So then we get that this function here, basically this guy, here, let's write negative h bar c squared integral 0 to infinity of r to the 4th, e to the negative r over a naught dr equals negative h bar c squared times 24 a naught to the 5th. Alright, now we've got, if we look on the other side of the paper, we've got this. We've basically solved for all three parts of this, so then we can put it together, and we get that our whole problem is going to be equal to negative h bar c squared 24 a naught to the fifth. I believe it is 4/3 and 2 pi. Yeah, 4/3 and 2 pi times 4/3 times 2 pi. And then we can plug in c back in here and solve the problem. But at this point, it's sort of just like adding numbers and sorting them out, and I think we're all mature enough to handle that on our own. Alright, thank you guys for watching this modern physics tutorial. If you want me to do other weird math problems or stuff like that, let me know.
Okay, I realized after doing this that some of you needed to know the actual answer, so yeah, this is just what things look like simplified. It's just negative h. Alright, you OCD people can go to sleep now.